Here we're going to discuss the first force involved with wind, pressure gradient force, or PGF for short. To start, let's refresh our memory on atmospheric pressure. Again, the definition I gave you is the weight of a column of air. A barometer is the actual device that we use to measure pressure. Just like with a thermometer, there's many different types of barometers out there, but one of the most common is a mercury barometer. How a mercury barometer works is that you have a dish with mercury, and then you place a glass tube in the center. As the weight of the atmosphere increases, there's more weight being pushed down onto the mercury, and it goes higher up into the glass tube. Therefore, you can measure how far up the tube it went to calculate pressure. Another thing that is important to know about pressure is that it does not vary much horizontally, but decreases rapidly with elevation. For example, mean sea level pressure, or the pressure if you were standing at the coast, is about 1,013.25 millibars. In Denver, the mile-high city, approximately 5,280 feet up, pressure is only 840 millibars. By the time you get to really high elevations, such as the top of Mount Everest, which is 29,035 feet, the pressure is only 320 millibars. Let's use this chart on the right to talk about horizontal pressure differences. The highest recorded sea level pressure ever was 1,084 millibars. Conversely, the lowest recorded sea level pressure ever, which was in a hurricane, was only 870 millibars. While this may seem like a large difference between 1,084 and 870, that's the biggest extreme. Notice it's not close to the difference that you see vertically. Now that you understand pressure, we're finally ready to talk about pressure gradient force. This is arguably the most important force when it comes to wind, and it is simply the difference in pressure over a given distance. The reason I say it's the most important force is because it drives all movement of air. This force is what actually initiates and causes the wind. Without this force, there would be no wind. And how it works is air always moves from higher pressure to lower pressure. Not only does this force control the direction of movement by air always going from high to low, it also controls the wind speed. Large pressure difference leads to faster winds. This is why hurricanes with such low pressures have really destructive winds associated with them. You may be thinking, don't the largest pressure differences happen vertically? We have high pressure at the surface, but we have really low pressures in the upper atmosphere as you put most of the atmosphere beneath you. So shouldn't we have this really incredibly strong vertical wind blowing us off the surface of the Earth? Well, we would, but there is actually a balance. This balance is called the hydrostatic equilibrium. And what it is it's the balance between the downward force of gravity and this upward pressure gradient force from the high pressure at the surface and the low pressure in the upper atmosphere. Another important thing that we have to talk about is how exactly do we get horizontal pressure differences across the Earth's surface? There's actually two ways in which this happens. The first way is thermodynamic, which means temperature causes it. The second way is dynamic processes, which we'll talk about later in the semester. To understand how temperature can create horizontal pressure differences, we're going to use something called the causal continuum. How this works is we think about how radiation differences are going to lead to temperature differences, and temperature differences will lead to density differences. These density differences will then lead to pressure differences, and we know if we have a difference in pressure, from high to low, we're going to have wind. So let's look at this in a step-by-step process, and use two locations, Texas and North Dakota. Based on my graphic, those lines at the bottom represent the surface. The dashed line labeled aloft represents some area above the surface. When it comes to radiation differences, notice I put a plus next to Texas. That's because Texas gets more radiation than North Dakota. This is because it's closer to the equator, and so it gets a higher sun angle, and thus less spreading of the solar beam and less path length, which are all things we talked about earlier in the semester. Because we have these radiation differences, there will in fact be temperature differences. Texas will be warmer and North Dakota will be cooler, represented here by colors red and blue. Because we have temperature differences, we're also going to have density differences. To understand this one, I've drawn a bunch of molecules into each of these columns. Notice that in both, there's more molecules at the surface than the atmosphere. That's because, again, gravity is pulling down towards the surface. In Texas, where it's less dense, you'll notice those molecules as a whole are more spread out compared to North Dakota, where it's more dense and those molecules are compressed in the column. Because of these density differences, we're going to have pressure differences. Now, if we think of pressure as the weight of the atmosphere, you may count up the molecules in each column and find there's 7 above Texas and 7 above North Dakota. So it seems there's no pressure difference. But if we look at this area of loft, you'll notice above this line there's still one molecule left above Texas and no molecules left above North Dakota. That means there is in fact a pressure difference. There's a high pressure over Texas and a low pressure over top of North Dakota. Air will blow from high to low. Thus we have wind. So perhaps we move that molecule above Texas over to North Dakota. If we do this, if we move molecules from the Texas column to the North Dakota column, this is going to create a pressure difference. Because we're adding weight to the North Dakota column, it'll have a surface high pressure. Because we're taking away weight from the Texas column, we're going to have a low pressure, and thus we're going to have a surface wind. This is the causal continuum. This is how radiation and temperature differences ultimately lead to horizontal pressure differences and eventually wind.